All right, so we got a chemical reaction going on here. Okay, so we got 2NO2, right, giving me 2NO plus O2 here. Okay, now I have two things to show you guys here. I got the table that has all my data in it, so I got my times and all that, and then I have the actual graph of this data here. Okay, so what we're going to see here is I want to look at what's happening to my concentration over time, right? And we understand now, right? We're looking at the reaction rates for each of my reactants and products here. Okay, so let's look at the table before we go to the graph over here. We can see, right, initially when we first start the reaction, I only have my reactant, NO2 over here at 0.01. And I haven't made any products yet. But we understand over time, right, this reactant will start to be consumed. And once it starts to be consumed, right, this is where we start to form our products. All right, and we can see, right, NO will increase over time with the products. And then we can see O2 over time increase as well. Let's look to how it looks graph-wise, right? Gotta show you the graph. Got to. So concentration, we got our concentration, which is gonna be on my y. We got our x-axis, which is my time, my seconds, right? And we can see, right, over time, my NO2, which is my reactant, like I mentioned over here, but we could just see it now. Over time, it's gonna go from this 0.1 molar to decreasing over time. And we can see what's happening here as it decreases over time. It just goes down and down. Now, as it's decreasing, our products are increasing over time. And once we plot this data, right, or you could use a table, either or, we can actually find a reaction rate, okay? And how are we doing that, right? We're just looking at the change in concentration over a period of time. All right, so if I wanted to look at the concentration change in this span of 110 seconds, I could find that concentration change, right? I could find this reaction rate. If I basically from this point here to this point here, right, 110 seconds. So in this 110 seconds, I know my change in time, right, from final point, initial point to final point. So final minus initial. And then I would just basically do the change in concentration here, all right? As I mentioned before, right? And, right, we can find that reaction rate with all of these examples, okay, well, all of them. So now let's look at the reaction rates, same data here, the NO2, NO, O2, what we saw here, same thing. So we got to understand, right, when we're looking for rates, the rate is the change in concentration over change in time. All right. So basically this delta is my final minus my initial, and this delta t is basically my final time minus my initial time. This is what we're always doing, everyone. We're always doing this equation here. Rates are always positive for product. Always. The rate for your product will always be positive. All right. So in this case, I got an example, concentration of my product, and then the concentration of my reactant, etc. All right, the reason why, is because we're making product. The rates will always be negative for reactants. Why is that? Because that's what's being consumed, right? We got to consume something to make something, all right? So we have to consume the reactant in order to make the product, which we see, right, in this example here. Right? We had to consume NO2 in order to make NO and O2, right? This isn't just going to appear out of nowhere, right? Something had to be lost in order for something to be gained. That sounds like a Marvel quote or something like that. I don't know. But no, that's real life, y'all. You had to lose something in order to be gained. As I showed you guys before where that negative come from, well, the reason why we have this negative here is because it's just easy and simple, right, to work with positive numbers. It's always easier just to work with positive numbers. So this is the reason why we put this negative here, All right, if you put the negative before the rate, all right, even if you have a negative rate, a negative times a negative will end up being a positive, okay? So let's look at an example, right? Let's look at my rate of NO2. You got the change in concentration over change in time. So your final minus initial, final minus initial. Let's say, for instance, right, I'm trying to figure out my rate of NO2 from a particular period in time. Initially, when we start to 50 seconds into the reaction, right? What is my rate during this time, right? What does that look like, right? That initial rate. And then just to show everybody from this to this. This is what we're trying to measure over here. What was the rate between my 0 and my 50 seconds? Final, which at 50-second mark is 0.0079. So plug that in there. Then I got my initial, 0.010, which I'm going to plug into here. So I got the change in concentration on my top, right, matching here. And then what do we do about the time? 50 seconds minus 0. So we're going to put 50 minus 0 here. And then once we do our math here, we're going to see that the rate, in this case, is going to be 4.2 times 10 to the negative 5. Molarity, big M, right, moles over liters, times seconds. Right, because the second's on the bottom. So basically, do not be shocked with the units, everybody. I just want to say this again. We got to know how we're going to use our units. Moles is on the top because this is molarity, moles over liters. And then because this is moles over liters, liters is on the bottom. But remember, our seconds will be on the bottom. So this is why we have to multiply them here. Units are key. Units are key here.